Okay, today we're going to learn a technique for solving equations that uses derivatives, and it's called Newton's method. And back in Newton's day, they used to have challenges between people. Somebody would come up with a new technique for doing something that would solve things quicker than anybody else knew how to do it. And then they would challenge the best mathematician of the day, say, I think I can solve 20 problems that look like this faster than you can. So they get somebody to make 20 problems look like that. They'd go in their separate rooms, they'd work them out. And anytime somebody came up with a new technique that was quicker, they'd win the match. That's how it works. So it's kind of like just out of pride. They didn't have TV back then. So that's how they entertained themselves. They had math competitions amongst themselves. Anyway, so Newton's method was a technique for solving equations that used derivatives and iteration. Now what Newton didn't have that we have is a cool calculator that calculates things really quickly. So he had to do all this calculation by hand, but he was pretty smart, so he was able to do it pretty quickly anyway. But just so you know, that's how things like this come about. And last chapter, or not last chapter, but 4.6, a lot of times we had a derivative that was a third or a fourth power, right? We had to use calc 0 to find our answers. I'm thinking for future years I want to put this lesson prior to lesson 4.6. I've probably said that in the past and I keep forgetting. But this will give us the ability to solve those equations without going into our calc 0. So it's just kind of a nice little thing. And Newton's method is just, it's a procedure. It's a step-by-step procedure, and this is how you do it. Let the function equal 0. So if it's like 2x equals tangent of x, move everything to one side so everything equals 0. Start there. So you get some function, set it equal to 0. Step 2, or step 1, after you get it to 0, find the derivative. Guess the answer, and here's how you guess the answer. I think the answer is 2. There's no, just guess something. It doesn't matter. I think the answer is 75.43. There you go. That's how you guess the answer. Then you use Newton's method to get you closer to the right answer. The closer you are to the right answer to begin with, the quicker it gets you there. But let's say the answer is 1.94 and I guess 2, I'd probably get it within 3 or 4 steps, 3 or 4 iterations. If I guess 100, I'll get it probably 5 or 6 iterations. It gets there pretty quickly. And iteration is this. Your first answer is the guess, and you get your second answer by doing the guess minus f of the guess over f prime of the guess. That gets you x2. To get x3, you do x2 plus f of x2 over f prime of x2. To get x4, you do x3 minus f of x3 over f prime of x3. So each time you get a new answer, that's the next thing you put into the formula, and then that. Whatever matches from one approximation to the next is accurate. For example, if I guess, let's say x1 is 2. Let's say x2 is 1.9741. x3 is 1.977, or 97, let's say 23. x of 4 is 1.9722143. x of 5 is 1.9722131. All right. So it'll kind of look like this. All right. Nothing's the same there, right? So no accuracy yet. All right. 1.97 matches 1.97. It's at least 1.97. 1.972 matches 1.972. It's at least that. 1.97221 matches 1.97221. It's at least that. So to get accuracy, once you get a repetition, all those digits are right, and then the ones that aren't the same still aren't right yet. All right. So then you just keep applying that formula, and each time you get a new repetition of digits, the next one might be x6 is going to be 1.972213091. All right. All of a sudden now we're accurate to 6 decimal places. Right? That's all there is to it. So it's easier to see it when it's being done than just to understand the sheet. But the sheet makes a lot of sense once we see it done. So let's just try it. Use Newton's method with the initial approximation x of 1 equals 2 to find x of 3. The third approximation of the root of the equation, 2x cubed minus 7x minus 3 equals 0. I'm going to do this one without a calculator. Okay, all we're doing is going from x1 to x3, but that's 2 iterations. It's easy enough to do without a calculator. All right, so The the original function, notice 2x cubed minus 7x minus 3 equals 0. So that's our original equation. That's what we're trying to solve. And again, this is the purpose for this. What is the solution to this equation? If that's the direction that you're looking for, I need to know the answer to this. The solution to this, Newton's method is a technique for doing it. All right? So knowing why you're using it is helpful. So, whatever's equal to 0 is what f of x is. F prime is just its derivative. Okay, so we have f and f prime. I know what x sub 1 is, and my job is to find x sub 3. All right? So x sub 2 is going to equal x sub 1 minus f of x sub 1 over f prime of x sub 1. That is actually what Newton's method is. That little formula there is his method. Whatever your guess is minus f of that guess over f prime of that guess. Now, f of that guess is just f of 2, so if I put 2 in place of all the x's, 8 times 2 is 16, 7 times 2 is 14, 16 minus 14 is 2, minus 3 is negative 1. F prime of 2 is just put 2 in place of this x here, 6 times 4 is 24, minus 7 is 17. So we get x sub 2 is equal to 2 and 1/17, and I lied, we're going to use a calculator. So, I don't want to do 2 and 1/17 for the third part, that's going to be ridiculous. So if I do 2 plus 1/17, what did I do plus?
2 negatives.
2 negatives make a positive. So x sub 2 ends up equaling 2.0588 23529. What matches? 2. So we know the answer is 2 point something probably, right? But 2 is right. All right, but nothing else is right. In fact, 2.0, but it might actually end up being 2.1 because you know that 5 would round that 0 up. So we're not quite sure about that. So if I want to get x sub 3, all x sub 3 is going to be is that number minus f of that number over f prime of that number. Do I want to type that number in 3 times? No. Absolutely not. So here's how we do this on our calculator as far as using the same answer. Now, I've got the answer key, so if I use answer, it automatically remembers that number, right? All right. How many times do I have to use that number? 3. All right. So what I want to do is I want to take the answer and store it as x. If I do that, answer store x, watch what happens anytime I hit x. It's that number. Alright, so the store key right above the on key. You can name it any letter you want to. I like x because I don't have to hit any alpha buttons. I just hit the x button. But I could also store it, answer store. I could store it as u if I felt like it. Now if I hit u, every time I hit u, oh, invalid dimension. What? Oh. There we go. Hit the alpha key, how about? There we go. Anytime I hit U, it's that number too, right? But I've already stored it as X, so it's X and U are both it, right? If I hit clear, it's still that number if I hit X. It's still that number if I hit U. So that's all the store button does, is you store some number, store some letter. Anytime you use that letter, that's going to represent that number. All right, so what I want to do is I want to evaluate this function and this function for this number, right? So watch how I do this. I'm going to type in x minus parentheses 2x cubed minus 7x minus 3 in parentheses. Ah! Why did I go out of classic mode? I was trying to show algebra 2 something and I forgot to switch back. Let's try this again. X minus parentheses 2x cubed minus 7x minus 3 in parentheses divided by parentheses 6x squared minus 7 in parentheses. All right. That's x sub 2, right? That's f of x sub 2 divided by f prime of x sub 2. All I have to really do is type in the functions there if I've stored x as my variable, as my number. So that gets me my next number, 2.056548769. more somewhere. X sub 3 equals 2.0565487769. Did it specify the number of decimal places?
4.
Oh, 4 decimal places. So 2.0565. That's what we end up with. All right. As far as what I just told you, we know the accuracy goes to the 2.05 level, right? And I might even approximate 2.06 because both 8 and 6 are bigger than 5, right? So I know for sure the 2.05 or maybe 2.06 is accurate for that. Let's try it out real quick. If I tried 2.06 into this equation, let's see. I'm going to just store that last answer as x, okay? And I'm going to type in 2x cubed minus 7x minus 3. We're trying to find out where this thing equals 0, right? And that's what we're trying to solve, equal to 0. And that's the approximate value we have for x right now. 0.00006. Pretty close. All right? So just keep that in mind. That's what we're doing. It's getting us closer and closer to the value of 0. All right?